Hi, in this Martin video, we'll be discussing important information on color. How does color affect people? Well, it can be determined that color has a psychological effect on people and that each person's perception is different. Different colors are used to convey certain moods, but how they affect one person may not affect another person in the same manner. For example, the color red is associated with love and passion, but also represents anger and intensity. When used in a nursery environment, this can be overstimulating to babies, so other colors can be used for more calming effects. Colors are often used in company branding to convey a certain emotional message that may represent that company. In the Color Emotion Guide, blue represents dependability and strength, which is used by 3 major brands in their logo: Dell, HP, and IBM. The use of multiple colors by companies, such as Google and Microsoft, represent diversity. The colors in the spectrum can also be associated with temperature. Colors specified as cool, such as green, blue, and purple, are usually calming and reserved. These colors are more subdued than warm colors. Because blue is the only primary color in the cool spectrum, it is combined with a warm color to create others. Warm colors consist of red, orange, yellow, and combinations of these 3 colors. These are usually energizing, passionate, and positive. Red and yellow are primary colors, but other colors are not created by combining them with a cool color, as they are truly warm. Many colors can have associations with events, emotions, cultures, and customs. Red depicts importance, like the red carpet at special events, or warnings and danger when labels are red. Outside of the Western world, in China, red is the color of prosperity and happiness. But in South Africa, red is the color of mourning. When certain colors are paired together, the relationship between those colors can present a deceiving perception. If you look at the larger squares with a red square in the center of each, they appear to be different sizes, but in fact they are exactly the same size. Because the background colors used here vary, it gives the illusion that the red squares are different sizes. Sometimes using the same colors, combined with others, can give the perception that there are more colors than what there actually is. In the image with the larger purple squares and smaller rectangles, the rectangles are actually the same color, but appear to be different, making it seem as though there are 4 colors rather than 3. The image below reveals that when the rectangles are positioned together, the center purple is only 1 color, not 2 different colors. In the context of color, it is important to understand that the physical perception of colors is subjective, and each person sees it slightly different. It's possible to get a different reading from the same color. For example, if a red apple was placed in sunlight, the invisible colors of that sunlight would be absorbed by the apple's surface, except any corresponding to red. That corresponding red color is reflected to the human eye, and a message is sent to the brain causing a perception that may be different to each person even though it's physically the same red apple. As discussed in the previous slide, the human eye and brain translate the light into colors. In the human eye, 3 types of spectral sensitive cells react on the RGB colors. Sir Isaac Newton observed that the color is not inherent in objects. Rather, the surface of an object reflects some colors and absorbs all others. Referencing an apple example, we perceive only the reflected colors or wavelengths from the surface of the apple, making it black when it absorbs all colors, concluding that red is not in the apple. The graph depicts the color blue as the most reactive or sensitive at roughly 450 nanometers, meaning that the human eye is more susceptible to blue, which can be more damaging to the back of the retina, while green and red are more pleasant for the eyes to look at. Within the millions of colors that exist, they are made up of 3 main attributes. Hue, which is the pure spectrum colors as referred to by the names red, green, or blue. Brightness, also known as luminance, is the shade or tint of a color, where shade is the darkness and tint is the lightness. Saturation, also known as chroma, is a measure of purity of a color, or how sharp or dull the color appears. This is particularly important when you're looking at color mixing. Some of the terminology on this slide was described previously, but here they can be further described by their units of measure. Wavelength, otherwise specified as color reflection, is measured in nanometer. The luminance intensity, measured in candela, incorporates brightness, also referred to as luminance, which is measured in candela per meter squared. This measurement is also called nit, and is measured perpendicular to the rays from the source. Low brightness adds to the perception of deeper, more saturated color contrast in video, whereas a good contrast image can be perceived as an image with higher brightness. An example could consist of low contrast being used for indoor and high contrast being used for outdoor. Temperature was previously identified as warm and cool colors, but with white color specified in the range of candlelight to pure sunlight, it is measured in Kelvin. In the anatomy of a CIE chromaticity diagram, it is important to note that all colors visible to the average human eye are contained in the triangular area of the plot, which depicts, in the color spectrum, how the human eye is capable of seeing colors along any line between 2 points that are made by mixing colors at the end of the points. The edge of that same chromaticity diagram represents the most saturated colors, whereas the colors at the center inside the triangular plot represents the least saturated. Additive color mixing, in terms of LED, results in a very saturated pink, which is as close to white as can be obtained when all of the LEDs are combined and that many colors are mixed together. However, with subtractive color mixing, when all of the colors are mixed together, effectively, black is obtained. But it actually isn't, because there is a light source behind it. The theory is that subtractive color mixing exhibits black when all primary colors are filtered, and additive color mixing exhibits white when all of the primary colors are combined. The color mixing used by Martin that is based on graduated cyan, magenta, and yellow is done through subtractive color mixing that filters out one of the primary colors, red, green, or blue. It filters out the unwanted colors, so the desired colors are obtained. Additionally, the filter's strength increases as they move into the beam, providing a very wide range of colors and shades. A color wheel is designed to change the color of the light by having multiple color filters mounted on that motorized wheel. Overlapping the CMY flags and color wheel will combine them to multiply the color options. A special mirror-like coating called a dichroic filter is used to reflect unwanted colors from the white light. It is necessary for the transmitted colors to be present in the source, as tungsten halogen lamps give bright red colors and discharge lamps give stronger blue colors. Color-correlated temperature filters are used to adjust the color temperature on the white color. In turn, this softens or creates a warmer color temperature. As mentioned in earlier slides, LED products use an additive color mixing system based on individually dimmable red, green, and blue LEDs. Adding amber or white LEDs gives a warmer color or brighter color, respectively. Additionally, by varying the intensity of each of the colors, a wide range of other colors can be achieved. This concludes this training. Thanks for watching, and we'll see you in the next one.